I'm Jim Ayars, agricultural engineer with the U.S. Department of Agriculture. Today I'd like to talk about agricultural water management practices under limited water supplies and some of the lessons we've learned from recent droughts. Today, what I'd like to talk about is factors that impact irrigation management and strategies that you can implement during periods of drought and limited water supplies. What it's not going to be is a how-to session. There's a lot of other seminars that have already been developed that provide very specifics by crop, and I would recommend that you look at those to try to get particular answers if you have individual questions about a certain crop. Before we go a little much further, I'd like to talk a little bit about what is a drought. And you can see the definition there is a shortage of water resulting from a prolonged period of abnormally low rainfall. Of course, here in California, we're really talking about snowmelt or snowpack, and so it's a lack of snow being falling in the high Sierra. So, contributing factors, certainly climate is the one that comes to mind immediately. The other thing I'd like to talk about a little bit is the fact that the shortage of water also results from some other impacts. So regulation is one that will be with us for a long time to come, and I'll talk about that a little bit later. The other part, obviously, in terms of shortage of water is municipal, industrial, and environmental demands, or at least these have to be taken into account when agriculture then begins to use water. And here what I'd like to talk about is if you look down through the list there, you can see that climate is a way of life in California. It's not going to go away. It comes back fairly regularly. Now, back in the 20th century, there was a long period between 1934 and 1976 where there wasn't a drought. But after that, you see we have droughts fairly regularly on a 5 to 10 year basis. And the duration could be anywhere from 5 to 10 years between the two of them. The other part that's on here is where we talk about the regulation, or I talk about regulation. And here we see the CVPIA, which is the Central Valley Project Improvement Act in 1992. And this was a regulation that was developed to provide environmental water for the San Joaquin-Sacramento Delta. And this will then take a certain percentage of the available water supply and direct it for environmental purposes. So after that period of time, we see not only climate, but also regulation are impacting the availability of water. You can see it's 2012, we're starting into what has been called the worst drought of California's history, or nearly to it. So we're talking about productivity, and from an agricultural standpoint, really what we're talking about is crop production. That's the goal of any farmer, is to produce a crop. And you see we have some alternatives here. Certainly with annual crops, field crops, this is one strategy. The other one is perennial and tree crops. And what are we trying to produce, basically? Is either biomass or a fruit. So when biomass, we talk about something like alfalfa or hay crop, where that part is the economic part. With a tree or a vine crop, then the fruit that you take off the vine is really what you're trying to grow, and that's the economic value. Of course, you still have to sustain the tree or the vine for future use and for economic purposes. And so the next part then, as the term comes up, water productivity. Oftentimes you hear the term water use efficiency. Productivity gives you a little better sense of really what you're trying to do. And this little equation just tells you, what is the ratio, the productivity is the ratio of the economic yield then to the crop water use. And the crop water use there is, say, evapotranspiration, but alternatively, it could be the total applied water or the beneficially used water. Any of those terms are commonly used for water productivity. So the other thing to really think about is that the goal is to maximize water productivity, and this doesn't mean that you're necessarily going to maximize the yield. As it turns out, research has shown that you have a production function where each increment of water provides you some sort of a yield, and at some point in time, that additional increment of water does not have the same value in terms of increasing yield. So to really maximize or get the most out of your water, you aren't necessarily trying to get a maximum yield. Another way of looking at it is we're talking about trying to get more crop per drop, and this, you'll hear this come up quite frequently. So how do you maximize it? Going back to the equation, so you have two terms, the yield or the applied water, and as you can imagine easily, you can vary one of those variables and hold the other one constant. So you could try to increase the yield by maintain the same evapotranspiration or T value, which would increase the water productivity. The alternative then is to try to maintain the yield and reduce the applied water. So these then provide us with strategies that we can look at. And in the simplest way of looking at it, the options are simply to improve irrigation efficiency, which would be the ET term, improve plant performance, which is the yield term, and also improve water management, soil water management. And in this term, we're talking about trying to use rainfall as a portion of the total water supply. So we'll take a look at these, see what kinds of things or what options exist to do this. One of the first things then, implement an irrigation schedule. One of the first things we talk about then is what the grower practice. There's a lot of research that goes on about looking at scientific methods, but the reality is most growers have a way of doing it. And in the various polls I've seen, one of the techniques, or the technique that's frequently used, is direct observation. And this direct observation then is simply going out, looking at the crop, deciding that it's stressed, or looking at the soil and deciding it's too dry, and then making some sort of judgment as to whether you're going to irrigate and how much you're going to irrigate based on those observations. Another way of doing it, other techniques that are used are, it's called a rotation or a calendar. And a rotation is simply, every so many days you're going to irrigate. And while that's a easy way to do it, it still doesn't provide you the kind of information you need in terms of developing how much water to provide. Rotation, another sort of variant on that, is a calendar. It's simply it's what day of the month or what month of the year it is. I know that in the past, on this day, I've applied this much water to this particular crop, and that's what you do. And so it works oftentimes in some areas of the world simply because the climate is so uniform that on the average, that might be a way to do it. But really what we're trying to move towards is some sort of a scientific-based method wherein what you're trying to do is calculate the crop water use based on the evapotranspiration, the potential evapotranspiration, or the potential water loss due to the energy in the atmosphere. And this is modified by a crop coefficient. You see the Kc. And this crop coefficient then is a representation of the development of the crop during the growing season. So what you can do is accumulate crop water use over a period of time, 2 days, 3 days, whatever your interval is. And at some point in time, then you replenish the water supply that the accumulated loss that you have. So what you've done is both created the time to irrigate and the depth of irrigation. And the information that you need to do this then you can get from the CIMMYS, which is the California Irrigation Management Information System, which will provide all the weather data and the ETO data. And you can look at UC publications that will provide the crop coefficient data that you need. And this, on a simplistic way, oftentimes is viewed as a bank account, or sort of a checkbook type of thing, where you deplete your checkbook by writing checks, or it would be similar to having the ET being lost. And when you get down to a certain level, you replenish the supply. Well, what about the other aspect of this then is irrigation efficiency. And this term is a representation of how well basically the irrigation system is applying water. The term that comes up most frequently is distribution uniformity. And the distribution uniformity is a characteristic of how much water is applied across the field. With a furrow irrigation system, you tend to have poorer uniformities than you would, say, with a sprinkler or a drip system. And this is because the difference in infiltration time at the head end of the field versus the tail end of the field with a surface system. And the distribution uniformity then, the poorer it is, the larger is the deep percolation losses. And that's truly, from an irrigation standpoint, your irrigation efficiency is going to improve as you minimize the deep percolation losses in a given system. The other aspect then is poor irrigation water management. This goes back to your irrigation scheduling then, providing the timing and the depth of application when it's needed by the crop. The other term, and I brought this up earlier, is then this idea of the ratio of beneficially used water to applied water. Now, in 100% irrigation efficiency, you would be providing just exactly the correct amount of water to replenish the ETO. But oftentimes you have an additional increment or additional requirement, and this might be cooling of the crop, you might have frost protection, and one most people are familiar with is salt management. And this is the idea that you're going to provide an extra increment of water then to leach salts out of the profile such that you don't impact the crop development. The reality of the situation is oftentimes most irrigation systems are not 100% efficient. So the efficiency, then the excess water that comes to try to manage the irrigation efficiency or to compensate for that efficiency, that's often adequate to meet the salt management requirement. The trick in all of this then is to decide how much water is required to be beneficially used, and then anything in excess of that then is wasted water. So that's another part of the challenge. Okay, what about the irrigation systems? The critical thing then is to have the proper selection and design for a given site. Okay, one of the things then, if you're going to have a furrow irrigation system, surface grade is absolutely critical. If you're going to effectively manage the system, it has to have the right furrow length. Oftentimes we don't think about the need to have an adequate water supply and the volume of water, because for a furrow irrigation system to be effective, you have to have enough head in a given furrow that you can move the water quickly across the field. If you don't do that, then the distribution uniformity falls off and you have problems. What about sprinklers then? Sprinkler systems, the critical aspects then are providing the right nozzle spacing, the lateral spacing. Again, you have to have the sufficient water supply to be able to run this. Then you also have to be able to have adequate pressure for the system. Drip systems, obviously water availability, lateral placement, design of the sprinkler, of the emitters along the lateral itself, having good filtration are all critical aspects of this. And then proper maintenance. You can have a very good system, but if it's not properly maintained, it will not operate the way it's designed. And without that maintenance, then all of your hard work is really for naught. Availability of water, brought this up several times, and the aspects of it are having water available when you need it. You know, it's one thing to say, well, I have sufficient allocation of water, but can you get that water when you actually need it? I mean, is it going to be on a demand or a rotation that we talked about, our calendar system? You know, even though you might have the correct volume of water, the problem is, are you going to be able to get it when the crop actually needs it? Because there are critical growth stages for this crop, and if you stress it at that point in time, productivity is lost. So even though you might have the correct amount of water, not having it when you need it is a really big issue. One of the things that comes up oftentimes is the idea of low versus high frequency irrigation. You find this more frequently discussed when you're talking about drip irrigation systems. And you know, a furrow irrigation system would be low frequency, you know, 1 to 2 week intervals between irrigation. High frequency with a drip system would be something like having, you know, multiple irrigations on a day, having irrigation, you know, every 2 or 3 days. So the difference is that you've changed the strategy, because no longer are you relying on the soil to store sufficient water to meet the crop demands. You're actually meeting the crop demand on a real-time basis, so you have the potential to certainly minimize the stresses that might develop. Non-uniformity. Well, we talked a little bit about non-uniformity from the standpoint of the irrigation system, but one thing I think we oftentimes forget is the spatial variability that exists within the soils. And this can have a large impact on your irrigation strategy. If you have two soils that have quite different soil water holding characteristics, one that will be a clay soil or stores a lot of soil water versus a sandy or a lighter texture soil that doesn't, how do you irrigate? I mean, are you irrigating to try to minimize the stress in the soils, the sandy soils, or minimizing the stress in the other, in the heavy soils? In one case, then you're going to have a portion of the field that will be less productive than another. And this then gets back to the idea of irrigation frequencies. And also the idea or the situation where you have a canal system or a piped water system. A piped water system simply, the Westlands Water District is a good example. And in this type system, water is in a pressurized system, basically available on demand. So you have quite a bit of flexibility in terms of the irrigation systems that you can use and how you manage those. A canal system is more typical of most irrigation districts, and there you have a lot bigger issues in terms of being able to get water when you need it and in the quantities you need it. I mean, it's harder, quite a bit harder to get it on demand, and it to some extent will limit the type of systems, irrigation systems, that you can select. We also need to think about the fact that drainage is an integral part of an irrigation system. And so really we need to talk about managing a drainage system then to provide additional water. There's a lot of research that shows in situ crop water use from shallow groundwater is a significant contributor then to meeting crop water requirements. What about agronomy? You know, we talked earlier about the idea of rainfall. So certainly, if we're trying to improve the storage of rainfall, we can take some lessons then from dryland farming. You know, so mulching the soil surface. If you have any crop residue, that can be mulched. Fallowing land. You know, using techniques that basically are going to reduce the total evaporation from the soil surface, and this then provides an additional benefit then for the crop. Other parts of the agronomy then, planting, fertilization, surface preparation. Certainly, you know, surface preparation with surface irrigation, you know, are these leveled, are the grades correct? You know, do you have a good seedbed preparation. What about cultivars? I mean, are there some cultivars that are better suited for limited water drought type systems? A lot of research looks at planting densities, as a way to offset, limited water supply. You might be able to change the planting density and still get an adequate yield. And the simplest technique simply is then to reduce the total area. I mean, if you have a limited water supply, then you can adjust the area that you're planting. Fertility management. This is an interesting area because, oftentimes people have talked about the idea of increasing some fertilizers then to offset some stress that you're seeing with reduced water supplies. And in the extreme, looking at precision applications of fertilizers and across the field. The other part I have here is the nitrogen, phosphorus, and potassium and micronutrients. But oftentimes we use the soil analysis as a way of characterizing or determining how much NP and K that we need to apply. And oftentimes it looks like they have adequate values of these particular fertilizer requirements, but the question is, how mobile are they in the soil, and in terms of being for the crop actually to use these nutrients. What I show here is the result of a fertilizer study. It was a water fertilizer study. There were 3 irrigation treatments. There was a high-frequency surface drip, a low-frequency surface drip, and SDI, which is a subsurface drip irrigation. And what I really would like you to see is what the effect was when the initial study just looked at nitrogen, and then they added some phosphorus to it, and then they added potassium. And you can see how much of an impact, regardless of the systems they're using, that simply adding that potassium fertilizer then increased the yield. This happened to be on a processing tomato plot, and the total applied water did not increase. So you're really looking then at increasing the productivity through very efficient fertilizer management. So this is something certainly to consider as you plot your strategies. And sociology, I always have to put this in there. And one of the things that we find when we talk to people is they say, I know how to irrigate. I learned, so I'm saying here, I learned at my father's knee, or somebody's knee, or somebody taught me how to do this. And my question is then, what were the conditions like when you learned to irrigate? Are you still irrigating the same crop? Do you have the same amount of water available to it? Are you using the same sort of irrigation systems? There's a lot that goes into irrigation that simply handling it down through the generations might be a disservice in terms of being able to very efficiently use irrigation water. And insurance. You talk to people and the idea that some water is good and a lot is better. And this really isn't true. I mean, some water, you need a certain amount of water to get the yield that you so desire, but after that point in time, then it becomes efficient, as I pointed out earlier, the idea of maximum yield. But even in the extreme, you can go and you get waterlogging and have severe impacts then on the overall crop itself. And political, and this is with us. I mean, there's no question that we have to be able to balance the social aspects with the environmental interests, with the agricultural interest. And in point in fact, a lot of research has shown as societies develop and become more affluent, water features are a significant part of what people like to do. So they like streams and lakes and rivers for recreation purposes, for simply relaxation. So, the environmental aspects of water management are critical, and it's something that we certainly need to consider as we go forward. Simply then, crop selection, that's a fairly straightforward thing. As I show you, it's either an annual or perennial. Well, the annual crops are fairly easy. You can either opt to irrigate them or not to irrigate them. So that's not a problem. The problem is then with the perennial crops, how are you going to approach water management with them? Because you have to irrigate to sustain them. There's no question about it. So the questions that you have to answer is to how much am I going to irrigate? Am I going to try to get a full crop off of it? Am I going to prune it? So, some of these other seminars can begin to answer those questions about strategies that you can use for perennial crops then to try to minimize, or when you have limited water supplies, what can you do? Additional considerations are, if you're looking at an annual crop, what are you going to select? You could be a cool season crop, which has a fairly short growing season, like lettuce, or some of the other vegetable crops that be grown in the fall or the spring, during periods of time when the water demand is going to be fairly low. You've got a short season, have a limited water requirement, versus a crop such as cotton or alfalfa or tomatoes that are grown during the summer, during the hottest part of the year, that are going to have fairly large water demand. So you have to select the crop itself and then make some judgments as to how much of that crop you're going to have versus other demands you have on the water. Certainly, sprinkler irrigation system selection is a critical aspect. Now, surface irrigation is quite typical. Over 80% of the irrigation systems in the state of California are surface systems, and we're seeing a lot of transitions from that. So one of the obvious ways to go is a sprinkler system, and you have either a hand-moved sprinkler system there, or in this case then a center pivot or some sort of mechanically moved systems. The advantages then on these systems are simply that you have a good control on the depth of applied water. You can get better distribution uniformities, and we'll talk a little more later about some of the disadvantages as well. The other way to go then is maybe from furrow systems or sprinkler systems, then progressing on up to drip systems. So we're looking then at either surface drip or subsurface drip. And there has been a lot more acceptance of drip systems simply because of changes in the equipment availability for designing these systems. You have a lot larger diameter drip tubes for laterals, which means that it's easier to lay the system out. There's quite a bit of flexibility. And a lot of the vegetable crops then, like lettuce that are shown there, use these systems very effectively. Interestingly enough, almost 60% of all the processing tomatoes grown in the San Joaquin Valley then are using subsurface drip irrigation, and the experience has been that they've seen yield increases from approximately 40 tons per acre with a furrow system up over 60 tons per acre using a subsurface drip system. And again, you're using the same or smaller amounts of water. So, reflecting back on how irrigation can be done and the water productivity, you see there we're increasing the productivity and maintaining the same depth of applied water. Okay, so what are all these changes? Basically, when you go from a surface system, which is a gravity supplied system, then to a drip or surface or sprinkler system, which are all pressurized systems, the first advantage is you have better control of the applied water. You also have the idea of, or the capability of chemigation. So you can apply fertilizers through the water stream and get a lot better distribution of that and better uptake, actually. That's oftentimes responsible for some of the better yields we see. So you have better irrigation efficiency, uniformity, potential reduction of applied water. better control on plant stress. And really that's the things we're looking for, is to try to improve the nutrition and minimize the stress when we're doing this. Of course, the disadvantage, the cost. I mean, certainly a drip system or a sprinkler irrigation system costs a lot more per acre than simply having to go out and grade the field then for a gravity irrigation system. So what this means is then you have to look at the idea of changing your cropping pattern then, so you get the additional benefit that can be associated with having these type systems. Another critical component then is this, to really make these systems effectively, is to be able to use them on demand. And so we're talking about having water on demand. And so a pipe system, certainly, that's not a problem. You know, when you have water delivered by canals, that's a bigger issue. And I heard recently that many irrigation districts, or some irrigation districts that are typically canal systems, are also developing sort of off-stream storages or capabilities that they can provide water on demand, because a lot of their growers are beginning to use drip irrigation system. And I think the most critical thing then is we have to learn new management. You don't manage a drip system the same way you manage a furrow irrigation system. And this is absolutely critical. To really derive the benefit from this system, you have to learn how to operate it properly and manage it properly to fully derive the benefits. One thing, and there's one of the seminars that talks at length about deficit irrigation, but this is the idea then, you're going to provide less than the full water requirement. Going back to that water productivity curve, then that's that ET part of it. So you're going to reduce that and try to maintain the yield. And so two terms that are frequently used, the idea of a regulated deficit or sustained deficit irrigation. The sustained deficit is simply the idea that you know what the water requirement is throughout the entire season, and what you're going to do is simply reduce the amount of water by a given percentage. So some work that Larry Williams did with Thompson seedless grapes, he reduced the water supply by about 20% of the requirement as he understood it to be, and found that it did not impact the yields at all. The other idea is a regulated deficit. And this concept is that you'll decrease the irrigation uniformly during a portion of the growing season, but there are critical times that you'll fully meet the crop water requirement, and this will ensure the crop development and the yield. So it's a little bit different. And we've got a little bit of some data here from a deficit irrigation project that we've got with grapes. And you can see the Sugar 1 on the left-hand side. You have both a sort of sustained deficit and a regulated deficit. The treatment 2 then is sustained at about 75% of the growers practice uniformly throughout the season. The T3 then is we reduce the applied water then to about 50% until half bloom to berry softening. Then we go up to that 75%, so it's equal to T2, and then it drops back down after the berry softening. And another critical aspect on this slide is look at the harvest dates. Now the Sugar 1 is a early season crop, so it's harvested in June, and which means that you have the entire summer then to maintain the crop, and this is an ideal time then to reduce the total applied water. So you have a strategy that you can deficit irrigate and still, you know, get a good crop out of it. The Crimson Seedless provides a different issue, and there we have the grower practice, which is the blue line. The other two then are regulated deficit we set from fruit set to veraison is to we maintain the full water supply, and then during either side of that then we reduce the applied water by either 80% or 60% of the the grower practice. But here, the challenge is that the harvest doesn't come till very late in the season, from like October to December. So trying to develop a strategy to deficit irrigate there is quite a bit different than the early season varieties. And this is basically a summary of the data. And the takeaway is that we could reduce the total applied water than the sugar one by about 15 to 20% and not have any impact on the yield compared to the grower practice. We got up to 30% reduction. There were some differences in yield, but anyway, it does demonstrate that we can deficit irrigate and still maintain the yield. The crimson seedless, basically the same takeaway message. We could look at 15 to 20% reduction in applied water. Yields are maintained. The interesting part of this particular study was that crimson seedless is a red grape, and color development then is critical, and the deficit irrigation improved the color development for the particular crop. Now, just as a summary then, I used the Westlands Water District to see how the farmers in that district then reacted to to limited water. So the period of time was from 2006 to 2009, and they went from 100% allocation from the Central Valley Project to 10% in 2013 or 2014. They have 0% allocation. The numbers that are interesting then are cotton. Went from 52,000 hectares or more down to 7,000 hectares in that period of time. Tomatoes, 37,000, only dropped to about 32,000 hectares. And lettuce, about half. And then we actually see that the amount of applied wheat increased by about a third during that period of time. If we looked at the perennial crop production in that same period of time, basically there were no changes. I mean, there's some changes shown, but there really wasn't a significant change in the total area being planted into almonds, pistachios, or grapes. The interesting number then shows that the fallow land was tripled during this period of time, which basically tells us then that we saw changing cropping patterns. We reduced the high demand crops, or high water demand crops, such as cotton, which does not have a high value. We maintained the high value crops, which is tomatoes, and then it's the winter crops, the wheat. We saw some increases there. The data don't show it here, but if you look around, you find that there's significant changes from furrows to sprinklers to subsurface drip. They're also interested in trying some dryland farming of some grains. So basically, when we're talking about adapting to limited water supplies, first thing really we need to do is to take a look at the irrigation systems, ensure that they're properly operated and they're properly maintained, because you can't begin to improve your efficiencies unless your irrigation system's in good shape. Then really begin to take a look at application of irrigation scheduling. Really refine the numbers or the way that you're taking a look at irrigating, trying to determine what the water requirement is and meeting that water requirement and doing it with the most efficient system that you can. So again, what are the options in terms of improving or changing to a more efficient system, going from gravity to surface type systems, or it's gravity surface systems to pressurized systems. And if you reflect on the frequency of drought, then assume that you're going to have a drought every 3 to 5 years. And what does that really mean in terms of what your cropping going to be? What is the balance between, say, the annual and the perennial crops, and what strategies would you develop to sustain the perennial crops? And finally, deficit irrigation when it's applicable. Certainly, there's a lot of interest now in deficit irrigation, and it would be part of an overall irrigation strategy.